In this calculus review tape, we're going to be going over differentiation problems involving trig, log, and exponential functions. You are supposed to have a list of all the differentiation formulas. This is available from the person who is running the lab where you get these videotapes. Okay, it is assumed that you have this list of formulas before you start the tape. Okay, the first example, y equals the sine of 3x plus 5. Okay, this is a fairly straightforward problem involving the sine of a function. So look on your formula sheets for differentiation formula for the sine of a function, and you'll see that it tells you to get the derivative of the sine of a function, its cosine of the same function times the derivative of the function. The derivative of 3x plus 5, of course, with respect to x, is 3. So the derivative of sine of a function is cosine of the same function times the derivative of the function cosine of 3x plus 5 times the derivative of 3x plus 5, which is 3, and this can be written as 3 cosine of 3x plus 5. Okay, now what if we change this problem slightly and we make it y equals sine of 3x plus 5 to the 4th power. Sine 4th, 3x plus 5. Okay, now some people, they see a sine. Anytime they see a sine, they want to write a cosine. It's just, I don't know, something inborn. Okay, you've got to fight against that. You've got to analyze the problem and say, what is this basically? And if you do that, you will say that this is really the sine of 3x plus 5, the whole thing raised to the 4th power. So if you ask yourself which formula to use, you don't use the sine formula to start. You use function of x to the nth power, f of x to the nth power. This is an example of the power rule. It's a function to a power. Don't let the sign bother you at the moment. Okay. So if it's a function to a power, you're going to differentiate it by saying the power, 4, times the function sine of 3x plus 5 to the 1 less power, which is 3, times the derivative of the sine of 3x plus 5. Power, function, 1 less power, derivative of the inside. But the inside itself is a problem that needs a formula. It's the sine of a function. And of course, it's the one that we just did. So let's see what we have. We have 4 sine of 3x plus 5 to the 3rd power can be written as sine cubed 3x plus 5. Now for the derivative of the sine of 3x plus 5, that's when you say the derivative of sine of something is cosine of the same something times the derivative of the something, the derivative of 3x plus 5, which is 3. Okay, so we have power, function, 1 less power, derivative of the inside, the derivative of sine of something, that is cosine of something, derivative of the something. And if you want to, you can write this as 4 times 3, 12, sine cubed, 3x plus 5, cosine of 3x plus 5. You can combine the 4 and the 3. Okay, so although they look, somewhat similar, you have to realize that they both involve sine, but this one starts off as a function to a power. This one starts off as sine of a function. So it's always to analyze it, to decide which formula you're going to start with. In our next example, we have y equals e to the tan 2x. We want to find, of course, dy dx. Analyzing this, we see that this comes under the category e to a function. So we look on our formula sheets for the derivative of e to the function, and it tells us the derivative of e to a function is e to the function times the derivative of that function. Derivative of e to a power is e to the power times the derivative of the power. Okay, so don't let the tangent bother you at the moment. It's really an e to a power problem. Derivative will be e to the power times the derivative of the power. Okay, now you say, well, what is the derivative of the tangent of 2x. It's the tangent of a function. And what is the derivative of the tangent of a function? Once again, looking at our formula sheets, the derivative of the tangent of a function is secant squared of that function times the derivative of the function, the derivative of 2x, which is 2. So it's e to the power times the derivative of the power, but the power is itself tangent of a function. And the derivative of tangent of a function is secant squared of that function, derivative of the function. So secant squared 2x times the derivative of 2x, which is 2. In our next example, we have the following. Y equals x cubed natural log of the cosine of 4x. Okay, so we have to ask ourselves primarily what kind of a problem is this? And we say that this is essentially an example of the product rule. This is like f of x times g of x. It is a product. So to find the derivative of the product, it's going to be the first, x cubed, times the derivative of the second, times the derivative of the log of cosine of 4x, plus the second, which is log of the cosine of 4x, times the derivative of the first, derivative of x cubed. First times the derivative of the second, plus the second times the derivative of the first. Now, when it comes time to differentiate the log of cosine of 4x, or the log of anything, we look on our formula sheets and we notice that the derivative of the log of something, okay, the derivative of the log of a function is the derivative of the function over the function. So the derivative of the log of cosine 4x is the derivative of cosine of 4x over cosine of 4x. The derivative of the log of anything is the derivative of that something over the something. Log cosine 4x, so it'll be the derivative of cosine 4x over cosine 4x. Log does not appear in here now. Derivative of log of something, derivative of the something over the something without the log. Plus now log of cosine 4x times the derivative of x cubed with respect to x, which of course is just 3x squared. Okay, and don't think that you can just multiply the 4x times the 3x squared. This has to either be written, both of these with parentheses, or you can move the 3x squared out in front. Okay, now derivative of the cosine of 4x has to be put there. And if we look on our formula sheets, derivative of cosine of something is minus the sine of the same something, minus the sine of 4x, times the derivative of the 4x, which is 4. So we have x cubed. Now for the derivative of cosine 4x, we have minus the sine of 4x times 4 over cosine 4x, plus rewriting it 3x squared, natural log of the cosine of 4x. And we can simplify this and write this as minus 4x cubed. If you have sine 4x over cosine 4x, you can write that as tangent 4x, or you can leave it sine over cosine, plus 3x squared natural log of the cosine of 4x. Here, if you want to put the parentheses around cosine 4x, fine. If not, it still has to be the same thing. It's clear that we mean the log of this whole thing. In our next example, we have y equals the secant of e the square root of x. Okay, now we have to ask ourselves, what is this essentially? Now, this is essentially secant of a function. Okay, don't confuse it with the one that we had earlier before we had like e to the tan 2x. This was e to a power. The trig function was not important immediately. It was e to a power primarily. This, however, is primarily a trig function. It's secant of something. Although the something involves e, we're not going to let that bother us at this stage. So we look on our formula sheets for the derivative of the secant of something, and we find out that the secant of something, the derivative will be secant of that something, tangent of that something, times the derivative of that something. Derivative of secant of a function is secant of the function, tangent of the function, derivative of the function. Okay, so we get secant of e to the square root of x times tangent of e to the square root of x. Now, derivative of e to a power. Well, we've had that before. The derivative of e to a power is e to the power times the derivative of the power. So we have secant of a function, tangent of the function, derivative of the function. But the function itself is e to a power. So how do we differentiate e to the power? E to the power times the derivative of the power. Okay. That's what we have. Secant of e to the square root of x, tangent of e to the square root of x, e to the square root of x. Now we need the derivative of the square root of x. Okay? If it helps here, let's think of the square root of x as x to the 1/2 power. Square root of x is x to the 1/2 power. This is x to the n. It's n x to the n minus 1. When you differentiate it, that is 1/2 x to the 1/2 minus 1, or minus 1/2 power. 1/2 x to the minus 1/2 power. Okay? And if you want, instead of writing it as x to the minus 1/2 power, we can bring it downstairs as x to the 1/2 power, or as the square root of x. Okay, so it's 1/2 x to the minus 1/2 power, which is 1/2. Now the x to the 1/2 power goes downstairs. Instead of x to the minus 1/2 power, it's x to the 1/2 power downstairs. And x to the 1/2 power can be rewritten as the square root of x. So we can write it as 1/2 the square root of x. And we can finish this up in the following fashion. We can say it's better if we put the e to the square root of x in front. We save ourselves some parentheses. E to the square root of x, secant of e to the square root of x, tangent of e to the square root of x, all over 2 times the square root of x. In our next example, all right, and we once again want to find dy dx. So we have to ask ourselves, what is the essential form here? And we say, essentially, this is a product. I mean, you see a quotient in here, you see a tangent, but don't let that throw you. It starts off, it's basically a product, f of x times g of x. So it's going to be the first, x squared, times the derivative of the second, the derivative of tan x squared minus 4 over x squared plus 4, plus the second, tangent of x squared minus 4 over x squared plus 4, times the derivative of the first, which is derivative of x squared. First times the derivative of the second, plus the second times the derivative of the first. Now, here the derivative of x squared, of course, is just 2x. In fact, if it looks a little ambiguous, you can simply move the 2x in front and make it 2x tangent of x squared minus 4 for x squared plus 4. Second times the derivative of the first, which is 2x times this. Okay. Okay, now here is the more complicated part. We have the derivative of tangent of something. Okay? Don't let the quotient bother you at this stage. We're talking about tangent of something. The derivative of tangent of something is secant squared of the something times the derivative of the something. Okay, derivative of tangent of anything, it's secant squared of that something times the derivative of the something. And at this point, we're going to need the quotient rule. X squared, secant squared of x squared minus 4 over x squared plus 4. Now, the derivative here, it's the derivative of a quotient. So it's going to be the denominator, x squared plus 4, times the derivative of the numerator. The derivative of the numerator is 2x, minus the numerator, x squared minus 4, times the derivative of the denominator, which is 2x, all over the denominator, x squared plus 4 squared, plus 2x, tangent of x squared minus 4 over x squared plus 4. And the only real simplification here would be you could multiply this out. You would get 2x cubed plus 8x. You'd get a minus 2x cubed and a minus a plus 8x. The 2x cubes would cancel. The numerator here simplifies to 16x. And that could be multiplied by the x squared out in front. Okay, but that's basically the best you can do on it. In our next example, we have the following. Y equals x squared plus 5 to the 6th power plus 6 to the x squared plus 5 power. And basically, what we're going to do is break it up, differentiate each little problem separately, and add the results. We can take the derivative of this and then add the derivative of that. Okay, now, this is in the form function of x to the nth power. Okay, it's in your chart. It's in your formula charts. It's f of x to the nth power. This, however, is in the form a constant raised to a function power. Okay, this is in your charts under the form a to the f of x power. Okay, the power rule, the f of x to the n, is only used when you have a function base and a constant power. Okay, if you have a constant base and a function power, you use the a to the f of x formula. All right, so here using f of x to the nth power, function to a power, so we're going to say the constant power times the function x squared plus 5 to the 1 less power times the derivative of the inside. Power, function, 1 less power, derivative of the inside, plus, now for the derivative here, the derivative of a to a power. Okay, it's a to the power, derivative of the power, log of a. Derivative of a to the f of x is a to the f of x, f prime of x, log a. A to the power, derivative of the power, log of the base, log of 6, natural log of 6. Okay, so this is f of x to the nth power, power function, 1 less power, derivative of the inside. This is constant raised to a function power, a to the f of x. It's a to the f of x, f prime of x, log a. Okay. Now, what about the following? This will be the last problem on this tape. Suppose I had given you x squared plus 5 to the sine 2x power. Here we have, once again, a power, but here we have a function base and a function in the power. And if you look on your differentiation sheets, it tells you to use log differentiation. if you have y equals, say, f of x raised to the g of x power. Okay, if one of them is a constant, either the power is a constant or the base is a constant, we have a technique of solving it. But if they're both functions, okay, then we're going to use log differentiation. Okay, so let's do that. Y equals x squared plus 5 to the sine 2x power. And the trick here is to take natural logs of both sides. The natural log of y is equal to the natural log of x squared plus 5 to the sine 2x power. And why do we take natural logs? Because it's a property of natural logs that the log of something to a power can be rewritten as the power times the log of the something. We can bring the power down in front, so we can make it sine of 2x, the log of x squared plus 5. So what was a function to a power is now here a product. The log of something to a power, it's the power times the log of the something. We have here a product. And now, at this point, we're going to take derivatives of both sides with respect to x. So we'll take the derivative of log y with respect to x equals the derivative with respect to x of this whole thing. Now, on the right, we have a traditional product to differentiate. We're going to get the first sine of 2x times the derivative of the second plus the second log of x squared plus 5 times the derivative of the first. First times the derivative of the second plus second times the derivative of the first. The derivative of log of x squared plus 5, of course, is derivative of x squared plus 5 over x squared plus 5, or 2x over x squared plus 5. Derivative of log of something, it's derivative of the something over the something. Derivative of x squared plus 5 over x squared plus 5, or 2x over x squared plus 5. Plus the second log of x squared plus 5 times the derivative of the first. The derivative of the first, derivative of sine of something. The derivative of sine of something is cosine of the something times the derivative of the something, or cosine of 2x times the derivative of 2x, which is 2. Now let's look on the left side. Okay. If this had been, well, we had over here log of x squared plus 5, and how do we differentiate it? Derivative of x squared plus 5 over x squared plus 5. So we're going to do the same thing here. Whereas y is a function of x. Okay, so it's going to be the derivative of y over y. Same idea. The derivative of log of something is derivative of the something over the something. That's what we did here. Derivative of x squared plus 5 over x squared plus 5. So here it's log of y. So it'll be the derivative of y over y. Okay, what does this mean? Derivative of y with respect to x. That's just dy dx divided by y equals, now we have 2x sine 2x over x squared plus 5. It's, if you write it the other way around, the 2x first, and you don't need the parentheses, plus 2 cosine 2x log of x squared plus 5. Now, you're not quite finished yet. We want dy dx. What do we have here? We have dy dx over y. In order to get dy dx, which is our object here, we will have to multiply both sides of this equation by y. Now, when you multiply by y on the left, it'll cancel out. When you multiply by y on the right, okay, you'll have the entire right side times y. But what is y? It's your original function. So your final answer will be, the y's cancel here, dy dx equals y, which is your original function, times this whole mess. So let me write down your final answer here. Dy dx is y, which is the original function, x squared plus 5 to the sine 2x y times this whole business, which is 2x sine 2x over x squared plus 5 plus 2 cosine 2x log of x squared plus 5. Now let's go through that just one more time. We started off with a function of x, okay, raised to a function power. Okay, this calls for log differentiation. We take natural logs of both sides. We bring the power down in front and turn it into a product. We take the derivative of the right-hand side using the product rule, the first times the derivative of the second plus the second times the derivative of the first. On the left here, we have the derivative of log of something. It's the derivative of the something over the something, which gives us dy dx over y on the left. Now, the question is to find dy dx. So therefore, we multiply both sides by y. It cancels out here. It reappears here. You get dy dx equals this whole mess times y being the original function. And that's what I have over here. Okay, the whole mess, 2x sine 2x over x squared plus 5 plus 2 cos 2x log of x squared plus 5 times the original function y. And that brings us to the end of this tape.